All right. So good afternoon, everyone. Let's start. Last Thursday we learned the gate level description in Verilog. So for small circuits, the gate level structural modeling approach works very well because the number of number of gates is limited. And the designer can use and connect every gate, every individual gates. Also, the gate level modeling is very intuitive to a designer with a basic knowledge of digital logic design. However, in complex designs, the number of gates is very large. Thus, designers can design more effectively if they concentrate on implementing the function at a level of abstraction level, at the level of abstraction higher than the gate, higher level. And this decorative or data flow modeling approach provides a powerful way to implement a design. Verilog allows a circuit to be designed in terms of the data flow between registers. So we describe the data flow between registers. And this is called this is why it is called data flow modeling. And a continuous assignment is the most basic statement in data flow modeling, in decorative modeling. It is used to drive a value into a net. Let me show you examples. So this is a 4-to-1 multiplexer in data flow description. This is the module multiplexer 4-to-1 data flow. It has terminals S, D, and Y. Y is the output. S is a 2-bit input. D is a 4-bit input. Well, now here is the statement, a main statement to implement this multiplexer in a data flow manner. The keyword is assign. It assigns something into Y continuously. So it's a continuous assignment. So whenever there is a change on the right-hand side, any signal on the right-hand side changes, and it will be reflected in the output Y. It's continuously assigned to the output Y. All the time. So it drives some value into a net. Now here, this implementation is this statement is like this. So it is a 4-to-1 multiplexer. Here is a truth table. The S is the selection. Basically, we have a multiplexer, 4 inputs. B0, B1, B2, B3, and a selection signal, 2 bits. Of Y. We're going to construct such a 4-to-1 multiplexer selection circuit. Okay, so D is the 4 lines of data. For conciseness, we just use a single variable, D3 to 0 with 4 bit Ys. Our Y is a Y with the is a single Y scalar. Now the 2 stables here. S is the selection signal, the 2-bit selection signal. If S1 is 0, 0, 0, then we pass D1 to the output. If 0, 1, then we pass the second line to the output. If selection is 1, 0, pass the third one. If selection is 1, 1, we pass the fourth line of D to the output. So it can be described in this logical, Boolean function. Say if the S1 is 0, if a 0, so this little wave is bitwise not operation. It's not S1 and not S0 is true, then we pass D0's value to Y. This is the first case. Or the second case, if is 0, 1, selection of 0, 1, we pass D1 to Y. This is an operation. It's like what? If this first part is true, then it's 1 and D1. 1 and D1, you can just means you pass D1 to the output. Or the next statement, next part of statement, and this little vertical line represent all function, or when S1 and not S0 are true, that means 1, 0 case. D2, this D is passed to the output, and lastly, when S1 and S0 are true, it's 1, 1 case. I pass D3 to the output Y. So this is a continuous assignment. Whenever a signal here changes, it will reflect output. This table shows those bitwise variable operators. This N represent bitwise N. This little triangle is bitwise exclusive OR. The exclusive NOR, the complement of XOR, is represented by this symbol. A triangle followed by a little wave, or a little wave followed by a little triangle. This is one way to describe or to construct or to model a multiplexer in the data flow manner. And here, the output left-hand side in this assigned statement must be a wire variable. We know we have 2 categories, wire and register. Left-hand side must be a wire. And for this ports of SDY, if they are not declared as wire or register, then the default value is wire. This 4-to-1 multiplexer can also be modeled in a more concise way using conditional operator. The same truth table. So this is another way. The same input and output here. Now the statement here, main statement, data flow statement here. Let's look at the way it implements. It uses a conditional operator. The conditional operator is the question mark operator. So here, let's see a part of question mark. The question mark here. It evaluates the statement before the question mark to see if it is true or not. If it is true, they will pass the first value after the question mark to the output. Otherwise, it will pass the second statement after the question mark to the output. So question mark and colon here. So first you check the selection input to see whether it equals to 0, 0, 0. Here we needed to specify the length of this binary number. Length is 2 bits, 2 pi b. If s is equal to 0, 0, then we pass d0 to the output. Pass d0 to y. Otherwise, we pass the result of following statement to the output. So the next statement is a compound statement. It's another conditional operator. So it check. So in here it checks if s equals to 0, 1. If it is true, pass d1. Otherwise, going down to the next conditional statement. The third statement is check whether s equal to 1, 0. If true, pass d2. Otherwise, pass d3. So lastly, last statement, last question mark here, last conditional operator. Check whether it equal to 1, 1. If true, pass d3. Otherwise, it pass something else. Well, you may wonder why we need this last expression here, because we have exhausted all the statements, 0, 0, 0, all the cases, 0, 0, 0, 1, 1, 0, and 1, 1. Why do we still need this? Well, here, this example is for the case when s is unknown. S has a value of possible values of 1, 0, x, z. So each bit can be these 4 values. Here we only cover those 1 and 0 cases, all the 1 and 0 cases. But in case s is unknown or high impedance, we just pass this unknown x to y. 1 bit unknown x to y. So this is some subtle thing here. Another way to implement this conditional operator, to this 4-to-1 multiplexer using conditional operator. Same input and outputs. The statement is more concise now. So y check it check first the S1, the S1 first. If it is 1, then evaluate this expression. If it is not 1, then evaluate the other expression. Let's see if S1 is 1. And this, then it look into S0. So if S0 is true, then pass D3. Pass D3 to output. Otherwise, pass D2. Return D2 value. And now here is the return value when S1 is 0. And we look into a 0. If S0 is true, 1, then pass D1. Otherwise, return D0's value. So this is a concise way to model the multiplexer in the data flow manner. So here you see this is a one abstraction level higher than the gate level. The gate describes the connection of individual gates, but here is one level higher. You don't need to care about those actual circuit structure. Just describe the functions and assign this value to the output. And in the process of synthesis, the EDA tools will automatically convert such description into logic gate implementations. So, are there any questions regarding this data flow modeling of a logic? If no, let me move on to a behavioral. The data flow is already like behavioral. Verilog provides designers the ability to describe design functionality in a higher level, in an algorithmic manner. So the designers can describe the behavior of the circuit in a very high level, like C language. The design at this behavioral level is very much like C programming. It's more like C programming than digital circuit design. And actually, behavioral Verilog constructs are similar to C language constructs in many ways. Well, there are two structures for behavioral description or procedural description. They are the same. The first one starts with keyword always. So use the keyword always to provide the functionality using a tiny program, not execute sequentially. It's procedural, step by step. And inside the always block, designers can use standard control flow statements like if, then, else, case, for loop, other things. And statements can be compound, can be nested. We use the pair of keyword begin and end to form a block. Here is an example. Adder. This is a just one bit adder. Input A and B, output sum and carrier are declared here. By default, it will be wire type, but now we declare the sum and carrier as register type variable, because here we are going to use them in a behavioral modeling. If you remember that within the always block, the left-hand side of a statement must be a register variable. So we declare some carrier to be register variables. They are scalar. Each of them is the 1-bit register variable. Okay, now we start with this always execute the following statement sequentially when this event occurs. The event here is not A or B. There is a change on A or B. So the two input, if any of the input changes, we will execute the following statements. Actually, we have seen this example earlier. Here, say, to produce the outputs, so we check the value of inputs. Say, we check whether A equal to 1 or when A equal to 1 and B equal to 1, the carry output will be 1. So if A equal to 1 and B equal to 1, carry will be 1. So after 5 units of delay, carry will be set to 1. You see this if statement is like C program. Else, carry will be 0. Here we only produce the carry output. Sum is not shown here, but you can add the lines here. So always the statement following to follows always here is this list is called activation list. The activation list tells the simulator when to run this block. It allows the user to specify when to run the block and makes the simulator more efficient. Two forms of activation list in Verilog. So you can put, you can give a list of variable names that may trigger the block. And you can you use all, this keyword all. Or you can use comma here. So let's evaluate this block when any of the named signals change, either change from 0 to 1, 1 to 0, or X to 1, X to 0, Z to Y, any change. We have 4 values for each variable, 0, 1, and X and Z. Or you can only specify one direction of change of signal change, say pulse edge, positive edge of a signal. If a signal rise from 0 to 1, or a signal fall, to make an edge triggered flip-flop. This can be to make an edge triggered flip-flop. E value is only on one edge of signal. But be careful here, the rise edge not only means 0 to 1 change. Rise edge of a 0 to 1, of course, is a rising edge. But 0 to X, Z is also regarded as a rise edge. And X are unknown and 0 to 1 is regarded as rise edge by the simulator. And for the following edge, 4, 1 to 0, 1 to 0 is of course a negative edge. And 1 to the X and Z, this is also a 4. X, Z to 1, to 0 is a 4 edge. Now here is an example to show some waveform to show the timing of activation. Now I have a clock signal phi, periodic clock, and an input signal like this. To illustrate the activation, here I give 3 examples, 3 outputs. Output A is from this example. This is activated when phi has a change. When phi has a change, it executes this statement. It assign the input, pass the in value to the out A. So let's check. If there's change here, phi has a change here, in is 0, so in is passed to out A. Then in the next moment, it triggers this always statement is this falling edge of phi. Now it evaluates input and pass it to the output. So output will change from 0 to high at this moment, at this falling edge of phi. Then the next moment of change in phi is this rising edge, and it passes the input value to output. Okay, so it generates such a waveform. Next one, phi here is low. Input is 0, so input pass the output. So and this is low, and so on. So that's for the first example. Then the second example, same activation is, but the statement is that we add a condition here. We assign input to the output only when phi is high. Okay, so it's just pass input to the output. Okay, you still check the phi. The phi is edge. This one. And then the second change on phi is here. Now, when phi changes, it changes to low. So if phi is false, phi is 0. This is false. So this statement will not be executed. So our B will keep 0, keep its original value. Now here we have a rise edge here. Phi is high. Okay, it statement is activated when and phi is also high. But so it will pass the input to output. But this time input is low. And low is passed to output. And next edge, phi is low, so it won't do anything. Then this edge, phi is high, so it will pass the input to output. Input is high, so input high is passed to the output. So our B changes to high here. Our last example, we have 2 variables in the activation list, phi or in. And the statement is that if phi is high in this event, if this under this event, if phi is high and pass input to output, you see, okay, first event is phi changes to change of phi here. Okay, and phi is high, so it will pass input to output. Output will be low. The next event is a change in changes from low to high. And phi is high at this moment. So it will pass input to output. So input high is passed to output. Okay, now you see that you have an asynchronous circuit. The output rises when input rises. It's not aligned to the clock. Then you can continue to check. Say here you have a falling edge in a signal. So this will also trigger, activate the always statement. But now the phi is low because if phi, so phi is false. So this statement won't be executed. The next change, next event is here. Phi from low to high. Okay, then it will pass the input because phi is high. It will pass the input to output. So RC will be 0. The next event here is the change in C. And phi is high. So it will pass input to output like this. These are some subtle things in the timing. You spend some time to trace it. So, are there any questions? Okay, so that's the always block. And the second procedural block is initial, or initial. We only have two blocks in two kinds of blocks in the procedural description, always an initial. The initial block does not need an activation list. Always you need an add something, activation list. Initial does not need. It's run just once when the simulation starts. It is used to do extra stuff at the very start of simulation. It can be used to initialize simulation environment. This is usually only used in the first pass of writing a design. Real hardware does not have an initial block. The always block will be synthesized into hardware, but initial will not. So best to use initial block only for non-hardware statements, like display. So for this is a table to compare the behavioral descriptions using initial and always constructs. So we'll keyword initial or always, and then following a block start as you use begin and end. Initial starts when the simulation starts. Always starts when activated. Initial execute once and stop, and not used in synthesis. Always is it continuously loop, like while loop, and is used in the synthesis. So the statements inside these blocks are executed sequentially, just like C program. And the data objects, new data objects inside a behavioral construct must be declared as a register. Like left-hand side of a statement inside this block, this concept must be registers. But right-hand side can be wire or register. I want you to distinguish the difference between data flow and this always assignment. Data flow is kind of continuous assignment, and the output and the output is driven continuously by the right-hand side of the statement. You know, statement say why you do something. The why is continuously driven on the other side. But in the procedural or in the always block, the output is not always driven by those signals. The output holds its value, and it will be updated only those activation lists triggered an event. So it needs to hold its value. It holds its value until the next event comes in and updates. So it must be of register type of variable. Procedural assignment. So the assignment within the always block, initial block, they are called procedural assignments. They update values of registers, integer, real, or time. Real time is also a variable. So the value placed on variable will remain unchanged until another assignment updates the variable. There are two types of procedural assignments: blocking assignment and non-blocking assignment. And blocking assignment are executed in the order they are specified, just like C program. You execute line by line. The next line will not be executed until the line before has been completed. So when you execute a line, the simulator will block other operations. Other lines will be frozen. It will only execute this line. So this is called blocking assignment. Block the operation of other lines. Block the execution of other lines. When you execute this line, just do this only, like a processor programming. Do this line. Other tasks wait, please, when I finish this. Just like a C program. Say I have a statement, say assign x to y, and wait for 10 units of time, delay for 10 units of time. So within this 10 units of time, nothing else will be happening. Other lines will be frozen. And in this blocking assignment, we use this single equal sign to do the assignment. Just one equal sign. For non-blocking assignments, use this symbol. It's the same as the symbol of less than and equal to. Less than and equal to. Here we assign x equal to y. And this indicates that it is a non-blocking assignment. It means when executing this statement, it does not, the simulator does not block the execution of other lines. Other lines can be executed in parallel. So it's called non-blocking. So this non-blocking assignments are used to model concurrent data transfers. Not take place after a common event. So you say if you have clock change, it drives many things and many flip-flops. And this you may use this non-blocking. Non-blocking use this less than and equal to sign. Well, it's the same. In a bitwise logic operation, we also have this less than and equal to this sign, but the simulator can tell if this is within always or initial a block, then it is treated as less than treated as a non-blocking assignment symbol. Now to see the difference, here is an example. Two illustrations. Illustration 1 and illustration 2. In illustration 1, we use blocking assignment. So here we always block. We look at the event of positive edge of clock. I have two always block. So in the first block, under this event, the program assign B to A. Then so it will the simulator will only execute this line first. So A is value equal to B. B's value is assigned to A. Everything else will be blocked. Now in this another OS block, it executes this assign A to B. Now because A is updated, A is returned back to B. So after this, after execution, A and B will have the same value. Because of the use of blocking assignment. In illustration 2, well, same construct except that we use this non-blocking assignment. Now, in the non-blocking assignment, the execution can be done in parallel. It means under this common event, under the common rising edge of clock, we do B assigned to A and A assigned to B simultaneously. This means a swap of the value of A and B. So after this step, A and B, they just change the value, and they should have different values. The content should be different. And this is probably what the designer wants to have. Because if you do the first one, you just need to if you want A and B to be the same, you do not need a second statement, a second always block. So there's some these subtle things as there's a blocking and non-blocking assignment. Non-blocking can be executed in parallel. Blocking must be sequential. When I simulator execute this, it blocks all the other lines, other parts of the program. Okay, I think I will stop it here for today.